Alright, so let's say that we have a rod. Alright, so I'm going to draw a rod here, and the rod is going to have a mass M and a length L. Right? So, pretty typical rod. Now, what we're going to do to this rod is that we're going to rotate it about its end. So maybe we're going to rotate it about an axis like this. We're going to rotate it something like this, right? So just typical rotation about its end. Now our job is to find the moment of inertia of this rod. So the question is, what is I rod equals question mark? What is that? Well, let's think about this. We know, I guess we should start from the basics, right? So we know that the moment of inertia of a point mass is equal to mr squared, right? Very easy formula. And that's just that. So moment of inertia of a point mass is something we know. Oh, we have a rod here. Rod is not a point mass. So it seems like that we're cooked, but we actually aren't cooked. Because see, we could think of a rod, right? If you think about it, we could think of a rod as like maybe a bunch of point masses. So maybe like point mass, point mass, point mass, just line them all up, and we should get a pretty good approximation of a rod. If we take one of these point masses, like over here, this little slice of a rod, we consider that to be a point mass. The point mass, the mass of it is going to be like a fraction of the total mass, so maybe we'll call that dm, right? If I'm saying too much, basically really small mass, we'll call that dm, right? Small slice, small mass, dm. And maybe what we could do is that this point mass is some L away, right? Some little L away from the center, from the axis of rotation, right? And the little slice is going to have a really small moment of inertia, so maybe it'll have some di, right? And using this formula, because the small slice we'll consider to be a point mass, we'll say that di is equal to dm L squared. So that's great. We know the moment of inertia of this really small slice. Now if we do that for every single slice that there is in this rod, smash all those di's together, well, we'll get the total moment of inertia of the rod. And when we want to smash infinitesimal things together, we always use an integral, right? This is not mathematically sound in any way, but like intuitively it should make sense. Or it kind of is mathematically sound, but whatever. Mathematicians will hate me. So we get that I is equal to integral L squared dm. Now, this integral, we have a little problem here because we're integrating L with respect to m. That's usually something we can't do. So what should we do? So here's the thing. I'm going to define a new quantity right here called density. And we're going to say the density is equal to mass over length. Now what this is going to allow me to do is create a relationship between dm and a dl that we probably want here. Because see, m is equal to rho dl, it follows from that really easily. So we could say that dm is equal to rho dl, where this small slice has a little length dl, right? And well, from this follows from that. So we can replace dm with rho dl. We'll get that I is equal to integral of L squared rho dl. Alright, so this is integratable now. And we're going to be integrating this from L equals 0, so it's the very beginning, to L equals capital L, to the very end of the rod. So integrate from 0 to L, right? And, well, the calculus here is very easy, just power rule. So I'm just going to say that, I'm just going to skip out on like the calculus details, but this is equal to rho L cubed over 3 from 0 to L, which is just equal to rho capital L cubed over 3. I actually didn't skip out on much. But anyway, yeah. So moment of inertia I rod is equal to rho L cubed over 3. But what we could do, we can do something else to simplify this. Right? Because normally you wouldn't want to calculate M over L like every single time. So what we could do is we could break this apart. So we could say the I rod is equal to rho L times L squared over 3. Using this, we can say that M is equal to rho times L because it's simple algebra. We get that I rod is equal to ml squared over 3, which is indeed the correct formula for moment of inertia of a rod about its axis, about this, whatever. About rotation of, doesn't sound like this diagram. Something like that. So yeah, moment of inertia of a rod, pretty simple derivation. DMs, DLs, DIs, they'll all help. This should work for most any shape, and if you like this video, well, feel free to like. If you didn't like it, respond. Put down in the comments what I could do better. I'll see you in the next video.